Cloud. All right, everyone. Welcome to Recitation 5. Today we'll be talking about CNNs and briefly go over the problem statement for part 2. And then we'll talk about some model architectures that you might want to look into for homework 2 part 2, some types of losses, and an example in Jupyter Notebook. So traditionally, this recitation would serve almost as a boot camp for homework 2, but now we have a separate boot camp for homework 2, so this recitation will be a little shorter than before. All right, let's get started. So the problem statement for homework 2 is you will be given 2 tasks. First is face classification. So given an image, you want to classify which identity or which person that face is. And this is very similar to what you were doing for homework 1 part 2, where you are given spectrograms and you have to classify which phoneme. It's the same classification problem, except you will be inputting images instead of spectrograms, and you'll be using CNN instead of MLPs. The second task here is face verification. So the idea here is that given 2 images, you want to run the exact same CNN on both. And then the goal is to figure out if the 2 images are of the same person or are of different people. So the way you kind of do that is you try to identify the most important features in the image that, as it's written, capture the identity of the face. And the way you do that is you run a CNN on both of them to get a feature vector that kind of summarizes the image, represented by a fixed length vector. And this is known as the embedding. And in order to do the actual verification, you need to take those 2 embeddings, one from each of the images, and then compute what's called cosine distance between them. And that's going to give you a number between, I believe, -1 and 1, and that'll be a measure of how similar the 2 faces are or how different. And yeah, we'll give you a bunch of image pairs, and then you'll compute the cosine distance between each pair of images features, and then you'll submit that to Kaggle for this part. And if anyone has any questions, feel free to raise your hand or just speak in chat. I'll try to monitor both as I go. All right. So yeah, this is kind of echoing what I said before, but classification is an n-way classification task, predicting from a fixed set of possible output classes. So in homework 2, we'll give you, I believe, 4,000 identities and a bunch of images for each, and then you'll train a classification network on them. And verification, we'll give you a long list of pairs of images, and you want to compute the cosine similarity between them. And this goes into a couple more details about the general verification task, where you're not just given pairs, but it's not necessarily relevant for this homework, so we'll just skip it for now. Yeah, this. Okay, so this is the verification task kind of visualized. So you'll first be given, let me see if I can annotate this. Okay. You'll first be given images, and then with the CNN, you'll be doing, the CNN is going to be doing face detection, and then you'll get the features from the CNN, and you'll get a feature vector corresponding to each image that you feed in. And then traditionally, you would have a big database of faces that you would also run the CNN on. So you have a feature vector for all of these faces as well. And then you try to look for this face, and this is our professor, by the way, look for this face in this face data set. So if Professor Biksha is in this face data set, the hope is that the feature vector of this image is very similar to the feature vector of his image in the face database. So those 2 images will have the highest cosine similarity, and then you could say, yes, Professor Biksha is indeed in this face database. And then you can figure out the person's identity that way. And this goes into some details about the open set versus closed set. I think the most important takeaway for this, as pertaining to homework 2, is that when you're training, you'll be given 4,000 identities and a bunch of images for each of those 4,000 identities. For the testing of classification, you'll be expected to classify images into one of those 4,000 identities. However, for the verification task, you'll be given pairs of images that are not in the original 4,000 identities. And the hope is that after you train a classification network for over the 4,000 images, your CNN would be strong enough that it can take in images not of the 4,000 identities and still be able to generate a representative feature vector from those images. So yeah, that's basically the summary of this. And to summarize that yet again, for classification, you'll be given a fixed set of 4,000 identities. For the verification task, none of the images will be from those 4,000 identities. Right, so next is transfer learning. So transfer learning is, it's not necessarily a complicated idea, but it's a really important and popular one. So it's the concept that you would train a model for one task, and then you would take the weights of that model and copy it over to the same architecture or a similar architecture and train the new architecture on a different yet related task. So the way it applies to our homework is first you have the classification task. If this is your CNN, and you train this for the classification task with, as you know from homework 1, you have a linear layer at the end, and then this outputs probabilities. After you spent a lot of time training this, the CNN here is actually a very powerful feature extractor, and it'll kind of be a waste if you just throw it away and completely retrain the verification task. So what you want to do is after you train the classification task, if you want to further do training on the verification task, you copy these CNN weights over, just this part, because this part pertains to classification only. You copy that over to another CNN, tack on another linear layer here to generate embeddings now. Let me just write that out here. Embeddings. And then train this with some other loss that you want. But the CNN back here has already been pre-trained through the classification test, so it will converge a lot better and theoretically generalize better as well. But as we'll see in the Jupyter notebook, it's not necessarily, you don't necessarily need to retrain for the verification task if your original classification network is strong enough. And you can just directly take the outputs right before the final linear layer as your embeddings. But we'll get into that later. Are there any questions up to this point?
So for the verification part, hello?
Yeah, I can hear you. Can you hear
Yeah,
me?
so for the verification part, we will be inputting two faces at a time in the CNN, right?
You will be inputting you'll take each face and put it into the CNN. So you have image 1
Mm-hmm.
and image 2, and then they'll each go into the exact same CNN. Like I think you talked about weight sharing, and this is kind of an idea of it. So these two CNNs will have the exact same weights, and then they will both output a feature vector. I should have drawn this out a little earlier, but here it is now. And then cosine similarity between these two feature vectors. And then this outputs something from range of -1 to 1.
Okay, so the first image in the CNN, this is from the 4,000 images which we have in the first part, right? And the second one is from the database of like 1 million or what?
Not exactly. So yeah, I'm not sure how much of this I need to cover in this recitation, but
Mm-hmm.
because there's going to be a pretty long boot camp about this,
Mm-hmm.
but I'll still try to give an idea for it since I think it'll be good to give a good understanding of this moving forward.
Yeah,
Uh,
can you draw it on the
yeah,
page?
let me share a whiteboard.
Yeah.
Uh, I see someone raise their hand. Let me address this question first because it's pretty crucial to this. So let's only think about classification for now. For classification, you have an image, just one image, and then you put it through a CNN network that you'll be designing. And then after the CNN network is a linear layer that outputs a probability distribution, as you saw in homework 1, probability distribution over 4,000 classes. And then you'll train with cross entropy loss. Whoops. Cross entropy loss. Right. So far there's basically nothing new in terms of concept. You just take images instead of spectrograms and then output identities instead of phonemes.
Yeah.
Does this part make sense, Tushar?
Yeah, that makes sense.
Okay. Now, the other task that you'll be working with is verification. And forgetting about the weight transfer or everything, the verification task is, let me not draw that first. Okay. So you have image 1 and image 2. These two are faces, and they're both from a data set of faces that don't include any of the 4,000 identities from the classification task. So image 1 goes into a CNN, and then a linear layer, which generates embeddings, like embedding, which is a fixed length feature vector. So let's say, I think a common number is like 256 or 512. So it's just a 256 length feature vector. For image 2, you do exactly the same thing. So you put it through a CNN, and then the same linear layer, and then embedding. And the thing is, these two networks have the exact same weights. So this is the weight tying or weight sharing that we talked about in lecture. So yeah, essentially you run the same CNN on two images. And then to figure out, to do the verification task, you put each of these into cosine similarity. And then cosine similarity outputs a range between -1 to 1, kind of representing how similar the two embeddings are. Does this make sense?
Yeah, this makes sense. So 1 and 2, these are from the data set, right?
Yeah,
Not from the data set, from the database.
yes, we'll give you a classification database and a classification training database and then a verification task database.
Yeah, but won't this take too much time? Because if you'll be having, like, let's say even 10,000 images in the database, then the combinations will be 10,000 C2, right?
Right, so there's a lot of research done on how to exactly choose the combinations, but yes. Okay, so you wouldn't like a single epoch wouldn't intuitively be like doing every single combination possible. It would be just making sure that each image is part of one pair.
Each
So
image.
when you select a batch from the data set, you will be selecting pairs of images, and then after you select that pair of images, you don't do those images again for that epoch or whatnot. But yeah, a lot of that's going to be covered in the bootcamp, so I think this is around a good place to not go into more detail.
Yeah, okay, cool.
And
Thank you.
another thing to remember is that we give you a classification database and a verification database, but the verification database we give you doesn't have, okay, I think it does have a lot of images, but then that's only for validation and testing. So you shouldn't train on it. And you should do this kind of identity matching training, or it's called metric learning or contrastive training on the classification database. And then the bootcamp folks will go over that more in detail.
Sure, I have just one follow-up question on this.
Mm-hmm.
So in the second part, you were trying to, like, match the images from the database. So is our objective to find as many similar pairs as possible in the database?
No, your objective is to, given two images that you don't know whether they're of the same person or not, figure out whether they're the same person or not.
So these two images you said we have to take it out from the database, right?
The classification database, yeah.
So is the classification, so does the classification database has like pairs of two images?
No, the classification database has 4,000 identities, and in each folder, there are a bunch of images pertaining to that identity. And then using that information, you can generate samples of like same people and different people and use that to train this network.
Mm-hmm. Now I get it. Thank you so much.
Got it. This drawing is a little nice to throw away, so I'm going to save it. Let's see. Okay. So yeah, I think there was another question. Deep, do you still have a question? Or I see you've lowered your hand, so I assume you're good.
Actually, I had.
Oh, okay, yeah.
My question is it necessary that we use the classifier network we train for the classification task as the network we use for the face recognition or the matching task, or can we also try different transfer learning with different networks, like the same concept of transfer learning but different networks as well? Is it allowed, or we have to stick to the network which is trained on the 4,000 images?
Okay, so let's see. Your classification network and your verification network don't need to be the same, but then to transfer weights from the classification network you train to the verification network, they need to generally be of the same architecture. Otherwise, you just can't transfer weights. It won't work because the architecture is different. So the weight matrices will be different. So there's no good way to transfer them.
Yeah, okay. The question is actually, can we use other pre-trained networks and experiment?
Pre-trained networks as in not trained by yourself, but like open source?
Yeah.
No. So yeah, that's an important point. So there are a lot of networks that are like pre-trained on ImageNet, Coco, Pascal, etc., like Cityscapes, Celebi, etc. You're not allowed to use any of those pre-trained weights. Yeah.
Okay, but I think
because,
that was
yeah, because part of this is like discovering your own architecture, experimenting with how different modules work. But if you do that, it just becomes like a fine-tuning task, which is not nearly as interesting as this.
Right. Okay. Got it. Thank you.
No problem. Let's see. When is the bootcamp starting? We'll be organizing a bootcamp. I think homework was released this Monday, right? Probably early next week, I think. Don't we need the verification data set to train embedding? You can generate. So to train the embeddings, basically if you want to do contrastive training, what I drew on the right side here, all you need are pairs of positive identities and negative identities, where it's like positive identities are like two images of the same person and negative identities are two images of different people. And you can generate that using the classification dataset because we give you a bunch of identities and a bunch of images for each identity. And the verification dataset that we give you is just literally a folder with like 50,000 images, and we don't tell you whether they're the same people or not. So there's no way to actually get ground truth for it. Okay. So hopefully this has given people a better understanding of the task. Let's get back to the slides. Recitation. Okay. So yeah. Next, we'll talk about some CNN architectures. So this is included here mostly for historical reference. You shouldn't actually use Alexnet, but Alexnet was the first. That's not true. It's one of the earliest CNNs that. Okay, I think it's safe to say that it's the CNN that popularized the use of CNNs in recent history, because yeah, it's the one that broke all the records of the more traditional methods like SIFT and stuff. So yeah, the ideas behind Alexnet are it uses ReLU activations between CNN layers to make training faster, implements dropout between layers, There's a lot of research about dropout in CNNs, and I recommend you look into it as well, but sometimes it helps, sometimes it doesn't. There's specialized dropout for CNNs, but yeah, some regular dropout often does not work very well. This is important. Data augmentation is a nice 1 or 2 line hack to get more points out of your model. And this network is trained using SGD with momentum. And generally for image tasks, it's more common to see papers use SGD than Atom or Adagrad or RMSProp. So I recommend you work with SGD. I think my intuition for this is if you just have just normal CNNs, you use SGD. And if you put like weird modules in there that aren't necessarily CNNs, you use Atom. But that's just my intuition. All right, VGGNet was a paper a few years after Alexnet, I mean. And then the idea, a couple of takeaways from VGGNet is that it stacked a bunch of identical convolution layers in blocks. So, and it also demonstrated the idea that CNNs must be deep in order to work well on visual data. And this is a common trend when designing CNNs. So you design a general block, and one of the most important parameter that this block takes in is feature size. And this is analogous to the size of the linear layer in MLPs. And then you have a bunch of these identical blocks, first with like feature size of like 64, as you see here. VGG has 2 CNNs here. And then you downsample, and then have the exact same block a few more times, but with like doubled feature size, so 128 and so on. And then VGG does that here as well. You can see 128. And then downsample, 256, 512. And then, okay, I mean, they don't increase it here, but you get the idea. Next, I believe, ResNet. So this is a super important paper because to explain actually, let me introduce it first. So we can ignore the bottleneck architecture for now. The most important thing about ResNet is this connection here. So basically, it takes in a feature map or an image, puts it through 2 or a couple of convolutional layers, and then you get an output here. And then the interesting thing about ResNet is that the output of this entire module is the output of these convolution layers plus the original input to the convolution layers. So let me say that again. You take an image or a feature map, you run it through some convolutional networks, and then for the final output, you add back in the original input, and then you take that to the next layer. And then this becomes its own block, and then you stack a bunch of these blocks end to end, and then train it end to end. Okay, so this is a super important concept. Does anyone have any questions on this? Okay, and ResNet. Oh yes, go ahead.
So
yes.
When you say you stack, do you mean so each block will be exactly the same architecture, but the output of the first block will go into the second block?
Yes, that's what I meant by stack. So like you would put them like sequentially in an nn.sequential class.
So each block will have the same x, and so each block will be x and then go through the convolution and then get an output and add back the x to that output and then go to the. But if that's the case, then when it goes to the next box, there's still a new x.
Yeah. So okay. Perhaps I don't think I was clear enough for that. So this is a single block. X is the input to this block, and then it gets added to the output of the convolution layers. So if you have another block in front of this that's doing the exact same thing, and then you get an output here, the output of this block is the X of the next block. And then so on.
Okay, I see. Thank you.
Right. And then when I say stack these, as I said, they're one after the other in an n not sequential block, n not sequential class. And these all have different weights. So you train them with different weights. I think I saw a question. Answer. How do we guarantee that the dimension of the input and output makes sure? Oh, okay. So that's a good question. Let me hold off on that. I'll talk about it when we get to the Jupyter notebook because what time is it actually? Yeah, we have time. I'll talk about it when we get to the Jupyter notebook because I have that an example in Jupyter notebook. Did a stacked conf share parameters or did they learn separately? So they learn separate parameters. So yeah, you don't share parameters between stacked convolutional layers. All right, so that's ResNet, and I'm not sure how much to go into the actual intuition behind why these are good, but basically what the authors of the VGG paper realize is that if you, as CNNs get deeper and deeper, you run into vanishing gradients or exploding gradients. And ReLU does help with this to some extent, but it doesn't completely resolve the problem. And the nice thing about residual networks, this residual connection, is that when you have gradients coming back from here, gradients have two ways to get to here. So it can go through the ReLU, the convolution layers this way, or it can just go through the identity connection here. And having two paths here strengthens the gradients because this identity connection makes it so that the gradients aren't reduced or changed at all through this identity connection when going from the output to the input. While if the gradient goes through these layers, then the gradient can either be decreased or increased. So yeah, having a bunch of residual connections allows for training of deeper networks, as this paper demonstrates, by trying to train something with 1,000 layers. That it wasn't cost efficient, but it still worked, which was a huge accomplishment then. And the other interesting thing about this is that if you have a bunch of these, well, okay, the idea is that since you're learning a residual, so like from X to the output, you're taking the original X and adding something to it. So since out is f of X plus X, only thing you're learning here is this. So you're learning a change to X that better represents the features. So you're learning a residual, basically. And there have been papers that talk about this being kind of like an ensemble, because if you have a bunch of these blocks, for each block, you can either choose to take features from this or this. And then for the next block, you have that same choice. So you end up having like 2 to the n different paths from the input to the output. And that's kind of like an ensemble of 2 to the n models. So yeah, that's some interesting things about ResNet, and it's still one of the baselines that you always try when you do any kind of image test. So it's really important to understand. Anyways, moving on. I think there was a question in the chat. Will you be showing what the combination? Yes, I'll be showing the example of a very, very simple residual block in the recitation notebook. Nice. Okay. DenseNets, we don't recommend you implement DenseNets, but it's here because it was in Bixha's lecture at one point, and it's kind of interesting. So DenseNets take feature map reuse to the limit. So basically, every dense block takes, in a DenseNet, each convolutional layer takes as input the outputs of all the convolutional layer outputs before it. And that's basically all you need to know about DenseNets, because it's not as commonly used nowadays, but it was just an interesting idea. Something in the chat. Would it be of any benefit to make such direct connections between stacked layers? I'm guessing this is in reference to ResNet. Wait, so benefit to make such directions between stacked layers. Sorry if I butcher your name, but Igly, could you clarify what you meant by the question?
Okay, so you mentioned that we're stacking multiple such blocks on top of each other, right? So say we have an X of like stack I, and we are connecting that X to stack, I don't know, I plus 3. Would that be of any benefit just to...
Oh, so like, are you talking about, we have a bunch of res blocks, and then maybe you add like this?
Exactly, yeah.
Yeah, okay. So yeah, I mean, this is kind of the idea behind DenseNet. It's not exactly, I'm not being completely true, but like, it's kind of the idea that it took all of these and concatenated here and used that as input to the next res block. And then for this, it was this, this. So yes and no. The simple one works very well already, so you don't necessarily need to do this, but I've seen papers of like, I think it was like ResNet squared or something that does something like this, but yeah, it's not commonly used. It's just an interesting direction for thought. All right, group convolutions. It gives better gradients, so I guess empirically it didn't improve performance that much, but yeah, I'm not sure about it. That's just a research direction. Okay, did you guys talk about group convolutions in class? I think I saw it for this week's quiz, but can someone see? Why are DenseNets not used? Wait, okay. Let me at least finish the CNN architectures like section, because yeah, and then answer the questions. Did you guys go over group convolutions or depthwise separable convolutions in class?
No.
Not yet. Okay. Just briefly talk about it. To talk about it then. CNNs. Okay. When you take an image and walk through a CNN, you get feature maps, and feature maps have a fixed number of channels. So the channels, and in a normal CNN, the channels of layer 1 or whatever layer are fully connected to the channels of layer 2. But what group convolutions do is they separate out, they split up the input and output channels. So this group of channels only is fully connected to this group of channels, this one to this, and this one to this. So if originally your number of input channels was 9 to 9, and let's only think about one by one convolutions for now. The idea is same for 3 by 3. But if you originally had 1 by 1 convolutions with 9 input channels and 9 output channels, you would have 81 parameters. I hope that's correct, 81 parameters. But now if you do group convolutions, you have 3 to 3, 3 to 3, and 3 to 3. And then now you would have 3 times 3 times 3, 27 parameters. So you've cut down on parameters by 3 times. And this is good for making efficient networks that you want to fit on, like, I don't know, like an Arduino or something. Okay, you probably couldn't fit into Arduino, but like for mobile networks, this is good. And papers that use this concept are MobileNet and ShuffleNet. And yeah, I'm not going into the details, but you can read the paper if you are interested in this. And okay, so you recognize this kind of architecture from before. It's the residual architecture. On the right is the bottleneck architecture proposed in ResNet, and on the left is the MobileNet V2 block proposed in MobileNet V2. So what the ResNet people said was, if you have a feature map with this many channels, okay, so first notice that there are 3 convolutions here. If you have a feature map with this many channels, if you reduce it to fewer channels and then expand that out to a larger number of channels, by forcing the network to encode the information in a smaller size, you're making the features more dense, or like you're learning stronger features, is what the ResNet people thought. And then by reducing here, since this is a 1x1 convolution, this is a 3x3 and a 1x1, this speeds up the computation a lot since you're doing the more expensive 3x3 convolution on fewer features. So this is what the ResNet people said. And then the bottleneck people said, not bottleneck, MobileNet people said was, well, for our architecture, let's try the opposite. So let's start with a smaller number of channels, smaller than this, and then expand it out and then shrink it again. And by extending this out, just for like expanding the features into a longer vector, you can learn more complicated relationships between the features before you condense it down again. And while this is normally very expensive with this expensive 3x3 convolution, they use what we saw before, group convolutions, to reduce the computation a lot. So they're able to do this. If you did this with residual blocks, you'll run out of memory probably. So yeah, these are two different ideas. You can experiment with both. I believe this is still more common, but yeah. All right, we're done with the CNN architecture section. Let me look at the questions. Okay, so why are DenseNets not used? I think people, okay, because DenseNets are an interesting idea, but ResNets are simpler and then they seem to work almost comparably. I think is the reason why DenseNets aren't used. And now there's more research done on this, so I can give a better answer. And another reason DenseNets are not used as much, I think, is for layer number k, you're taking as input a bunch of earlier layers, right? So at layer k, you need to keep in memory the feature maps of all these layers so you can add them here. And the more of these like you have to keep in memory, obviously you use more memory and then the computation is slower. And then when you port this architecture to another device, perhaps not well as optimized as this or not as strong as this, these end up being quite a bit of overhead that you just don't want. So that's one reason for DenseNet. Like even ResNet, you have to store the input until you process the output. And even for ResNet, there are papers that try to get rid of this and just collapse everything to convolutions. But that's just research. Okay, won't that affect the training and accuracy? I'm not quite sure what that means. I think I lost context for that, but yeah. Can you explain again what's 3x3 convolution? So I think this is covered in last recitation, but if you have a feature map like this, a 3x3, okay, and this is your output feature map. A 3x3 convolution looks at a 3x3 patch of the input feature map, multiplies it with the corresponding 3x3 weight matrix, multiply the two, and then add everything, and then put it into here. That's a 3x3 convolution. What's the difference between a squeeze block and an expansion block? Squeeze block and expansion block. Oh, yeah, so it's kind of what we talked about before. So an expansion block, why am I drawing it right? This expansion block takes a smaller number of features and then expands it out to a large number of features with the 1x1 convolution. And then this larger number of features is the input to this transformation block. While the squeeze block, that was the expansion block. Now the squeeze block takes a number of features and then squeezes it into a smaller number of features with the 1x1 convolution. And then this smaller number is into the 3x3. Does the side direction of these two structures mean adding original feature directly to output. Yes, this is the residual connection that we talked about before. So you take the input, do some processing, and add back the original input. So you learn a residual.
Well, so so is that what it means? The shape of the input and output should be the same. Because, yeah.
We'll talk about that when we get to Jupyter Notebook.
Okay, thanks.
Wait, when does this recitation end normally? 9:50, right? Wait, is it 9:40? I think. So we still have time. All right. Okay, so that was a long introduction to a bunch of CNN architectures, and I believe the newest paper in this list is like 2017 or 2018. So there was like 2 or 3 more years of more improvement after this. And then to list a couple for people who are interested in looking into this is ResNet. Okay, I think this is like 2015 or 2016 still, but this is ResNet, but like almost strictly better, but it's also slower. ResNet, and then RegNet. This is actually quite new. This is like 2020, I think. And it's a ResNet, but with optimized channel sizes. And then ResNest. This is close to state of the art on ImageNet. And then this is really complicated to implement, but it's just nice to see. I'm not sure if anyone will actually end up implementing this, but this will get you good performance for sure. Like using modules that are introduced here. SENet is another direction that uses attention in CNNs. And if you're familiar with attention or want to learn more about this, it's an interesting thing to read. And besides this, there are obviously like thousands of other papers, but these are the ones that I would, yeah, at least for now, these are the ones that I would recommend just reading for fun. And the ones that are covered in this paper as well. And then covered in this PowerPoint as well. I think I saw another question. How does the block to squeeze or expand? Okay, so the question I believe is, how can a 1x1 convolution squeeze or expand? So the 1x1 convolution only refers to the height and width of the kernel or the filter that you convolve over. So this is your input feature map. This is the number of channels. This is that's width, and this is height. And your output would be something like similar. Let's just look at a squeeze block. This is number of new channels, and this is the height and width. So the 1x1 convolution means that you only look at this single pixel and its channels here to get this single pixel. And then you can like, yeah. So a 1x1 convolution only means that you only look at a single pixel to get the outputs of a single pixel. And you're free to change the channel dimension in any way you please, because like the way I like to think about this is your base, like this here is just a single vector. And then this is also literally a 1D vector. So you're basically doing an MLP over this vector to this vector. So as you know about not an MLP, a single linear layer from here to here. And as you know about linear layers, you can change the number feature as you want. But a 3x3 convolution would take as input this entire 3x3 patch to get this single output here. And that can be thought of as a linear layer if you collapse this entire thing into a really long vector and got this as the output. All right, I can see how ResNet can improve gradient vanishing, but how would it solve gradient exploding? Huh. Okay, I mean, okay, that is a very good point. How would it solve gradient exploding? Actually, maybe I think I might have made a mistake when I said gradient exploding, because mentally I just grouped the two, gradient vanishing and exploding together, but I can't exactly see either why ResNet would help with gradient exploding. But traditionally, gradient vanishing is generally a bigger problem. So ResNet does help in that aspect, which made CNN training a lot easier. So yeah, sorry about that, guys. At least for now, I don't think I don't think ResNet would help much with gradient exploding. But gradient exploding is much less common than gradient vanishing. Gradient exploding would be dealt with bachelor and gradient clipping as such. Yeah, so you would do that, but I don't think ResNet specifically helps with that, like the residual connection. Sorry about the confusion. Okay, so we have just a few more slides left in this, and then we can get to the Jupyter notebook. So yeah, so discriminative features. So thinking back to the classification, the verification task, and we talked for like 40 minutes after it. So just a brief refresher. Classification task, you take an image, try to put it into one of the 4,000 identities. Verification task, you take two images and try to figure out whether they're the same person or not by getting two embeddings getting an embedding from each of the images. So a separable feature, as shown on the left here, is enough for classification. Because if this is identity 1 and this is identity 2, it's enough to be able to separate them with a decision boundary, because I mean, you just need to classify them into the same right bucket. But this is more important for verification, because if this is the input image 1 and this is input image 2, you're not just okay with being able to separate them. You want to figure out, since they're of different identities, you want their features to be like as far apart as possible. So the cosine similarity metric says they're very distant. So not only do you want to separate them here, you also want to like make this margin as big as possible. And people who are familiar with SVMs will kind of understand what I'm talking about here. Yeah, so not only do you want separable, you want the two features to be separable, you want them to be far apart from each other if they're different classes. And if they're of the same person, you want them to be as close together as possible. So that's what discriminative features are. You have maximum interclass distance, minimum intraclass distance. All right. Center loss. To be honest, we've recommended center loss as something to try for like the past 2 or 3 years, but a lot of students have had difficulty with this. And before I get into what center loss is if you want to use center loss, you have to use center loss from the beginning of training of your classification network. You can't train your classification network and then add center loss and then train again. It won't work. It'll just reduce performance. Again, you have to start training with center loss when you start training your classification network from like random weights. Okay, now that I got that out of the way, basically, I'm not going to go too much into the formula, but just try to explain this visually. On the left here is this is a standard MNIST example. MNIST, if you're not familiar, is a digit classification task where you have a bunch of images from that are each like someone wrote 0 through 9, and so you have 10 classes. So if you train with cross entropy loss only, you get a bunch of classes that are indeed linearly separable, but they aren't discriminative enough. If you train with center loss, you see that they're in their own patches, so they've maximized distance between classes and minimized distance within classes. And the way center loss does that is, along with training the weights of the CNN, it also trains a couple additional parameters. So there's a center here for every single class. And during training, it tries to, like each center has a corresponding class label. And then during training, along with training cross entropy loss, it also tries to minimize the distance between individual samples and the center of their corresponding class. So if this is the center for number 3, it tries to pull together all the samples for number 3 close to the center. And the center itself moves to be closer to where the center itself moves to be closer to where samples of the number 3 are as well. So it's kind of like a pull push thing. All right, that's central loss. And there are a bunch of other losses of contrastive learning as well. I'm not going to go into this. I want to get to the Jupyter notebook, and Bootcamp will cover this. And here are a bunch of links to the papers that we talked about in this presentation. And if you, I guess, go back on the recording, you can also see the couple of papers that I listed, which was ResNet, RegNet, ResNet, and SCNet. All right, are there any questions on the presentation before I get to the Jupyter notebook? All right, if there are no questions, I'll move on to Jupyter notebook. All right, so in this notebook, we'll be talking about a custom data set and the image folder data set and the data loader. We'll have an example of a residual block and a CNN model with a residual block. We start with some normal imports here. And then in this recitation, I've provided, well, I put together a subset of MNIST because the original MNIST dataset is like 200 megabytes, which is kind of annoying to download. So yeah, I think the main instructive purpose of using a custom dataset for this is to show how annoying it is and why you shouldn't do it if you don't have to. So, I mean, you can go through this code if you want, but it's not necessarily. It's mostly here for reference. But there are cases when you need a custom image dataset if you have more information than images, for example. But it's mostly easiest to just shape your dataset folder directory into the format that whatever repo you're using wants. That's for outside, but for this homework, we recommend you use image folder. So yeah, I mean, if you don't use image folder, you have to make your own dataset class, parse the data, you walk through this data directory and then save everything that ends with PNG, and then you construct the dictionary. I believe this is a dictionary between the 0th class corresponding to actual class name, 1st class corresponding to actual class name. Kind of annoying. Image folder does this for you. And then you can see that there are 5,000 images and 10 labels. Yeah, and then so on. Each image is 28 by 28. Now there's a lot easier way to do this, and that's just to use image folder. You just give it the root directory, and you can look at the PyTorch documentation to see what folder it expects directories to be in. And you can specify a transform here. And you should always have this, I think. It converts the image into PyTorch tensor. And this is also where you would add data augmentation techniques. And you can look into those in the Torch version. Not repository, Torch Vision documentation. So you initialize the image folder dataset here, and then you put that into a data loader, and then specify batch size, shuffle the markers, and you see that we have 5,000 images with 10 classes. And this is a lot less painful than doing this, so I recommend doing it this way. But if you do contrastive learning, you'll have to do something like this, I think. There's a question in the chat. What's the name of the function again for loading in the images? Could you clarify your question? Well, if I try to,
You said instead of building your own, was your own data loader and going through this manual process, there's something else that we could use. I didn't get that.
Yeah. That thing is just the image folder dataset class here.
Oh, okay. Thanks.
Okay. Now we see an example of the residual block that we've been talking a lot about. So this is the simplest residual block that you can have, and I've done this so you have practice implementing more complicated versions, because it'll be obviously good practice. Just to give you a thing to look at while going through this code. So you take input, you put it into conv layer, and then batch norm, and then I'm gonna leave this blank for a bit, and then you add these two, and then you do ReLU activation, and then that's your output. Instead of drawing a circle here, I'll draw. All right. So I drew the drawing. So it's basically exactly what the drawing is doing. So you have the first convolutional layer, and then the batch norm layer, and then you do something with the shortcut connection here, and then you have the ReLU layer. And in the forward, you put X through the convolutional one layer to get out. You put out through this VN layer to get out. And then you also put X through the shortcut layer to get the shortcut connection. And then you add the output of this and the shortcut and put that through a ReLU and then return the output. So yeah, that's a residual block. And I promise that I'll talk about what happens when the input size and the output size don't match. And that's right now. So you know that a feature map has 3 dimensions. Let me actually draw this in order though. Ignoring batch size for now, it will have channel dimension and then height and then width. If you use odd kernel sizes, like odd as in not even, and use proper padding, these should never change. Wait. Okay. I don't know why I just said that. That's not true. These should not change as long as you don't downsample. If you downsample, these will change. As for the channel size, almost all the time, the output of your block should be of the same channel dimension as your input. So you don't have to worry about this for now. Only worry about height and width. The thing is, if you downsample within the block itself, the input height and the output height will be different. And ignoring the parity issue, we'll just say that you downsample once here, and then your output becomes h/2 w/2. Then just adding an identity connection here will fail because the input has different height and width than the output. So what you want to do is have a little, in your shortcut connection, also have a convolutional layer if the input size and the output size are different. But different from this, which is traditionally a 3x3, this is just a 1x1. Because the only purpose of this is to make the dimensions match. It's not to do any extra computation. It's just to make the dimensions match. And you can see that here. If your stride is 1, you just do the identity connection. This is basically, it takes input and directly outputs the input. It doesn't do anything. However, if the stride is not 1, you have a 1x1 convolution with that stride, so the input and output are the same. And then this ensures that the shortcut connection is the same dimension as the output. Are there any questions regarding this? Okay. I wish I had explained this a little better because now that I think about it, I shouldn't have been adamant about the channel size not changing. Because sometimes you would have the channel size change from the input to the output, especially if you're downsampling. So if that's the case, you would also put in the new channel dimension here and also have a 1x1 convolution here. So the input and output have the same height, width, and channel size. And yeah. Okay. So that's a simple residual block. You should work to extend this by adding bottleneck or the other inverse bottleneck, whatever paper you try to reference. And the classification network here is just basically a bunch of these stacked. So it has an initial convolution to take it from the number of input features. For RGB, this is 3 to 64, and the batch term ReLU, and then a couple of these blocks, and then an adaptive average pool. So basically, this is let me draw this again. If this is your feature map, this is 64, this is height and width. You want to somehow get this into a linear layer, and the linear layer expects a fixed number of parameters while your height and width can change. So basically the solution that people have come up with is to have the linear layer here expect as input a 64 length vector, and then to completely collapse the height and width dimensions with average pooling. So this becomes 1 by 1 by 64, which you can then flatten to get rid of the 1 by 1 dimensions to be just a 64 length vector, which you can put into a linear layer. And the final linear layer takes the 64 length vector and then outputs the number of classes. This is the classification network. All right, so the actual training now, you initialize the data set of data layers as you did in homework 1. Number of epochs, number of input features, RGB, so it's 3. Learning rate, weight decay, number of classes. You want to send it to CUDA, initialize your classification network, send it to CUDA. Set your criterion as cross entropy loss for training classification network, and your optimizer is SGD. And then this is the most typical training loop, and then this is just an example here, and you end up with 96% accuracy after 10 epochs. And I bet if you train this for longer and tune the learning rate parameters, you can end up with 99, but I didn't do that. Okay, so that was the classification network. Really briefly on how you might extend this classification network to a verification network is you can take the features right, you can chop this part off, take the features right after flatten, you get a 64 length vector, and you can take that as your embedding of whatever image you put in. And what I recommend is first just try training classification network, see what accuracy you get, and then you chop off the final linear layer and then take the vector right before it as your embeddings and then use that to evaluate the verification task and see what numbers you get. If your numbers aren't good enough for the verification task, you might actually want to look into further training with contrastive loss. But if your numbers are good enough for the verification task, then you don't need to do that. So this is a general workflow that I recommend. All right, so that is basically it for the material I prepared.
So do you mean that for the verification task, we actually don't need to train anything? Is that what?
If your classification network is strong enough, it's possible that you don't need to train anything for the verification task.
So we'll just, okay, so how do we set the cutoff of the cosine similarity?
Okay, yeah, that's a point of confusion for a lot of students. And I'll make a really long Piazza post probably about the actual AUC or something metric that we use, but you don't do anything to the cosine similarity outputs before you pass it into Kaggle. You take the raw float value from -1 to 1 for every single pair and just put that in. Like like when I was a student, I've tried to threshold it, I've tried to modify it, scale whatever. I don't think I've done a single thing that actually improves my Kaggle score this way. So you should just take the raw cosine output and then put that in.
Okay, but aren't we supposed to, like usually when we train a network, we train and then we verify and we do it on a test set, right? So for the verification task, if, for example, our network from the classification is so good that we do not need to train anything, do we need to verify anything?
Well, what do you mean verify? Because you would need to do the verification task regardless.
Yeah, so you mean, okay, so we don't need to train the network. We can just directly proceed to validation. Sorry, I mean validation. So we can skip the training and we directly proceed to validation.
Yeah, you can directly proceed to validation of the verification test or the testing of the verification task.
Okay, so if the validation is good enough, is there a, and then we need to do it on a test set and we just directly submit the raw cosine similarity to Kaggle. That's what
Yes.
you mean.
Yes.
Okay.
In chat, a question about the residual block. If you apply 1x1 convolution on circuit with the same stride in your example, how can reduce W and H to half? Okay, yeah, that's if the stride is, yeah, okay, someone answered this. That happens when the stride is greater than 1. Can you explain how we can save the CNN weights so that we can transfer them to the verification task? Saving the weights would just be what you did for homework 1. You would just do torch save of model.state dict, I think. Model.state dict. And then, I mean, you can try loading in this whatever you saved, and then look at the actual, okay, yeah, it would save everything. And I mean, the easiest way to do this, at least what I would recommend is, where's the model? Okay, so let me just make a big block to explain.
You can actually chop off the last layer using slicing.
Yeah, you can chop off this layer using slicing, or you can do something like this. Like when you make a classification network, you can have everything up to the flatten in your nn.sequential whatever, and then have a final linear layer like this. And you can do features equals the layer x, and then equals, and then you can have an optional parameter here saying return embeddings. Let me just name this embedding. Else so yeah, this easier way to define the network. So like when you did a classification task, you would have return embedding be false, and you can just train it like this. And then if you want to try the verification task, you can pass in return embedding true, and then get the embedding. And then this way you can save all your weights, load them easily, and then just get the embedding. Does that answer your question, Bigly? Okay. Are there any other questions? If there are no other questions, or you have lingering questions, you can ask them at Piazza. If there are no other questions, I think that's about it for this recitation. Thank you for coming, everybody.
Thank you.